Okay, so can you just confirm if my voice is audible?
Yes, audible.
Okay. All right, so maybe I will get started. Let me share my tab and so that we can start. So, is my tab screen visible or not? Because it seems that it is not visible.
It is not.
Yeah, let me try again. I will rejoin maybe from this. Okay, it is connected to. Hi. Okay, I think now it is visible. Okay. Okay, so uh, uh, maybe let me create a new sheet. So this has to be tutorial 6. Okay. All right. So uh, yeah. So hello, namaste, and welcome everyone. Welcome to this tutorial. Uh, I have some work today, so maybe I won't wait for people to join. So I will start right now. And as people come in, maybe if they have some doubt, they can ask. Otherwise, we will continue. Okay. So, so this is tutorial 6. Okay, so this has to be tutorial 6. So in last tutorial, in particular, last week in week 5, what we saw was something called principal component analysis, right? And what we particularly observed was, we essentially saw that dimensionality reduction is something that we need. Okay, it is a crucial thing. There is I mean, the curse of dimensionality exists, and we cannot ignore the dimensionality of our input space, and we should try, always to reduce the dimension of the input space as much as possible, right? So uh, so we saw, so last time basically what we saw was, mathematical formulation of PCA, and we solved week 5 assignments as well. Apart from that, we, through questions, we also saw that, how PCA actually helps in dimensionality reduction. In particular, we saw, that what is expected from PCA. PCA does exactly that. It captures the directions of maximum variance by using the SVD, or eigenvalue decomposition, or of the covariance matrix, and using that we project our data onto the principal components to reduce the dimensionality. In some sense, principal components are the directions of maximum variance, right? And since uh, the maximum, and it is our hypothesis or assumption in some sense that direction of maximum variance uh, 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 should capture the sort of gist of the data in some sense, summary of the data, if you want to call it. So, but however, is it so to motivate autoencoders, which will be today's topic? Maybe we can look at pitfalls of principal component analysis, which was not yes, which was not discussed in the uh, lectures, but maybe I will try to give you some intuition to that. So let us consider. So okay, so let me first draw something. So okay, this is a sort of ellipse. Okay, so here are your data points. Okay, here are your data points. So what PCA will basically do is capture the directions of maximum variance, right? And what are the directions of maximum variance in this particular diagram? You could see that the data is spread has a spread. What is the direction of maximum spread? Perhaps this direction, right? This direction, this particular direction has some spread, right? It is elongated in this direction. Okay. However, there is another direction which you can see has some spread, which is this one, right? So this direction and this direction, right? And if you do PCA and calculate the eigenvectors and all those things, you would be able to see that the two principal components. The first one would be this particular direction, and T2 will be this will be the second principal component, right? And so let's say if you want to decrease, so this is in 2D, right? This is in R2. If you want to reduce the dimension of your data by, let's say, from you want to convert it from R2 to R1, maybe you will map your data on this P1, right? You will project all your data points on this P1, right? And you will say that okay, this is my new data and which has some reduced dimension, right? This was what it was, right? So this was the gist of PCA last time. But we should always ask these questions that okay, this is fine, looks good, and mathematically we have some guarantees. But is there any case where this will fail? In other words, is can there be some situation in which the direction of maximum variance does not capture the gist of the data? So let us look at it. Okay, I mean, let's try to create a example where PCA is not good enough. Okay, so for that, what I will do is I will do something. Okay, let us see what. So so consider the following. So instead of having just one cluster, assume there are two classes. Okay, so this is the first class. This is uh, the second class, right? Okay, these are so there are data points here, a lot of data points, and there are data points here. Okay, okay. So we have these two data points. Let's call these classes maybe C1 and C2. Okay, so these are the two classes. And again, I want to reduce the dimension. And so my ultimate goal is to classify the data points in C1 and C2. But someone comes and says me, oh, your data is in R2, right? This is again in R2. But I want some data points in R1 so that it is easy for me to classify and do stuff. So I would say okay, fine. I know something called PCA, which reduces the dimension, and I will use that to get you out of your misery. So what I will do is I will do compute the direction of maximum variance. So this is the first direction. I hope you will agree that if you see the two data point as just one cluster, one big cluster, so this will be the direction of the first max. So this will be the first direction of maximum variance, and this will be the second direction of maximum variance, right? So again, this will be P1 and this will be P2. And since our goal is to reduce the dimensions of this given data set, what I will do is I will project all the data points onto P1. Okay, I will convert R2 to R1. Okay, So I will say, all right. So this goes here, this goes here, this goes here, this goes here. This goes here. All these things are so. I am projecting the data points of class C1. But similarly, you can also project. You will also project the classes data points of class C2, which are these points, right? I am denoting those lines by red points. Okay. Okay. So these are again, projected here somehow. All right. So it looks a bit clumsy, but you will get my point. So okay. So this is my. Right. So this is my first point of class C1. This is second point, third point, fourth point, fifth point. Dot dot dot. Okay. And similarly, I have some points of my class C2, which is this one, the red points that I am drawing. Okay. And I hope you will start seeing some issue with this. Earlier, when the data was in R2, this was a separating hyperplane. In some sense, I can see easily that, okay, these two classes can be separated. However, as soon as I applied PCA, my data now is very clumsy and it is not separated. And hence I have lost the discriminative features of my uh, of my data set. Okay. So this shows this is just one example where PCA, although it works, PCA has done its work. The PCA does exactly what it is supposed to do. However, the end goal, it is not useful for my end goal, which is the classification task. All right, is that clear? So I hope you get my point that applying PCA naively is not always a good idea, and maybe it depends on what my end goal is. Okay. So having said this, this was just an example where PCA fails. Okay. So let me just write it down. So here, this is one example. So this was an example where PCA works. Okay. So we are good. But this is an example where PCA, although works, although works, is not useful. Okay. Why is it not useful? Because I have lost my discriminative features, that discriminative summary from my data set that I originally had. Okay. So having said this, this is in some sense motivation to go to deep learning or autoencoders. That will be today's topic. Okay. So the today's topic is mainly something called auto encoders. Okay. So okay, so what are autoencoders and why are they necessary? So the gist of it is always coming up with some mathematical solution or mathematical way to reduce the dimension might not be efficient enough. Okay. So people have tried to so people wanted to come up with some certain ways in which where you can actually let go of the mathematical ways and use deep learning to reduce the dimension itself. And this is a branch of deep learning which is generally known as something called representation learning. Representation learning, where you try to learn a representation of your data using deep learning methods. Okay. So autoencoders in some sense is the one of the most primitive works in this area of representation learning. All right. So what is an autoencoder? So here is a example. Okay, so maybe I will add some color here. So you have some data. Okay, copy, paste, copy this, paste it again. Okay, all right. Yeah, so maybe another two neurons. Yeah. So this is like my final layer. What I need is an intermediate. So, okay. Just give me some time. I will just draw it up quickly. Uh, Change the color of this to some blue. Again, copy this, paste it here, and change the color from this to maybe pink. Okay. So here is the gist of an autoencoder. What an autoencoder does is it takes some input, xi as input, okay, input to the. So this is a network. This is a neural network where these are, these networks are connected to each other in a general in the general fashion that we have seen till now. Okay. So what it does is it takes some data xi as input. It computes some intermediate representation h, okay, and after h it tries to decode or reconstruct the data that was given to it, and we call it xi hat. Okay. So so this is the idea. So this is something which is very intuitive. So what you are saying is that uh, there is a neural network. Okay. You are giving it something to it as input. Okay. And it is saying that, okay, reconstruct the same output. Okay. The output of this neural network should be same as the input. Okay. So there is no classification or anything like that. Okay. It is just saying that whatever is given to you, reconstruct it. Okay. However, in the intermediate layer, you are saying that, okay, just you deliberately reduce the size of the intermediate layer so that hopefully you will be able to learn something meaningful in the intermediate layer. Okay. So in this diagram, you are saying that, okay, I'm giving you some input xi, just give me the same xi as output. Okay. I don't want any classification or anything like that. I want the reconstruction of the given data. However, you are deliberately using a intermediate layer which has less number of neurons in it. And why have you done it? Because you are expecting that, okay, this xi hat is going to use h, it is going to the it is going to use the values of h to reconstruct the data xi hat. Okay. So in some sense, if it is possible to reconstruct my data xi hat using h, then h should be something meaningful. This is all it is saying. Okay. It is not possible to construct my xi hat using trash or anything which is not meaningful. H has to be something meaningful, otherwise I cannot reconstruct my xi hat. And how are we ensuring that h is meaningful? We are asking it to giving we are asking that, okay, h should be meaningful because I am constructing my h using xi as the original data. I hope the idea is clear. Okay. If not, maybe you can just unmute yourself and ask questions. Okay. So, mathematically speaking, what is h here? H is some activation function g. Okay. Uh, Remember, the basics of neural network, that you have a linear affine transformation and consequently, you have an activation function that is applied to it. So you have g into w times xi. So affine transformation. Okay. So this is the affine transformation part, and you are applying some so to say activation function on it, right? Similarly, your xi hat, what is it going to be? It is going to be some f, again some activation function of w star, which is some weight matrix again, h w star h plus c. Okay. So W is this vector, this matrix that you will use to compute H from Xi, and W star will be this matrix that you will be using to construct Xi hat from H. Okay, so this is the whole idea of autoencoders. Okay, there is nothing fancy to it. I hope you are not scared or anything with it. Okay, because it is a very simple thing. If you are scared, then maybe you should get your concepts clear by asking questions or any doubt if there are any doubt. Okay. So this is the whole idea of what we call as autoencoders, right? Further, there you can do interest. What is the good thing about these autoencoders? What are the good things? So in my opinion, the best the most important thing about this this autoencoder is that there is no handmade handmade uh, you know what do I want to say, application of autoencoder. Right. So, yeah, let me come to it. So, what I wanted to say was, okay, let me write it as follows. So, bluntly speaking, what is the best part of autoencoder is you need not worry about what it has learned, what it has, what it has learned. Okay. So, so this is the best part about autoencoders, right? So you just train your neural network. Okay, you don't need to know what the intermediate layer here is. Okay, I mean what it has learned, you need not worry about that. If you remember in PCA there was a lot of maths, and you knew that there are eigenvectors that are involved, and essentially you are projecting your data onto these eigenvectors, and it was a lot of complicated thing. But here, look, it is saying that okay, you need not worry about all of those things. Just do run this algorithm using this network, right? And essentially, eventually, you will learn something which is meaningful. And the best part about it is that you don't need to know what it has learned. I mean, you need to worry about it, but you did not learn. Okay, are these H, actually the eigenvectors? Are these, something weird or whatever? It can be anything. It can be some non-linear transformation. Anything. You need not worry about that. So, in my opinion, this is the best part about autoencoders, right? All right. So, uh, maybe what I will do is I will start. Uh, So you are asking autoencoder will have same number of input and output in Xi and Xi hat. Yeah, that is correct. Uh, so why should it be? Just think of it, right? I want to reconstruct my data, right? What I want to do is I want to take something as I want to take something as input, and I want to recreate it. Okay. So if this dimension is less than what is here, it means that I will never be able to reconstruct it, right? I mean, at least the dimension should be same. Otherwise, there is no hope of reconstructing the same thing, right? Am I clear? Is like Am I making sense, or is it not clear? Maybe you, right? Okay. So that is the reason, right? So let's say you are given a vector here in, let's say, some R10, okay, 10 dimensional vector, and you are saying that okay, in my output layer I won't make it R10, I will make R6. So there is no way that this R6 will be same as R10. I mean, these vectors will not match eventually. So that is the reason this has to be R10. It cannot be R6, and hence the dimensions need to be same. Okay, that is what reconstruction means. Okay, reconstruction means you have to exactly replicate what is given to you as input, and that is only possible if the dimensions are same. Otherwise, there is no hope of creating the same thing. So maybe now I will. Is there anything? So so maybe while doing questions, we will discuss these things. But let me just summarize the type of autoencoders that were mentioned in the lectures. So one of them was under complete autoencoders. Uh, there was something called over complete autoencoders. There was something called sparse autoencoders, and there was something called sorry, contractive autoencoders, right? So each of these autoencoders had their, own special properties and things like that. While doing questions, I will explain all of them because I think some of the questions require explaining those things. So while doing questions itself, we will discuss these things. Okay. So if you ask me, this is a very simple thing. There is nothing more to it than understanding the concept. The rest of the things come from what the basics of deep learning that you saw in maybe weeks like week 3 or week 4. Okay. So let's start with the questions. Let me just open that questions, right? Okay. So let us start doing questions. Okay. If you have any questions, conceptual or anything, you can just ask those questions, or maybe I will be seeing on the screen. I will be seeing the questions that are given. So maybe if you type something, I won't be able to see it. However, I will keep coming back to this page, Teams, and see if there are new questions. If there is something urgent, then maybe you can unmute yourself and directly ask. Okay. So here goes the first question. So this is assignment 6, right? So, okay, so here is the first question. The first question asks you, which of the following networks represents an autoencoder? Okay, so there are four options. Let me draw these options. Okay, so I won't draw the connections. I will just draw the input and output layers. Okay, so so in the first option there are three inputs. These three inputs, there are two intermediate layers. Okay, and there are one, two, three, five output. Three, four, five. Okay, this is the first option. So can this be a autoencoder? Well, as you had just asked, that the dimensions of the dimension of this layer and this layer has to be same. Otherwise, it cannot be an autoencoder because this thing cannot be reconstructed using this thing, right? I mean, it can be if you just take these three or something like that, but in general, this is not true. Okay, this is not an autoencoder. So I mean, I will just straight away, say that this is wrong. Okay. So what is the next option? The next option says one. So there are three inputs, there are three intermediate layers, and there are two outputs. Oh, sorry, I changed the color. Sorry. So there are three intermediate ones and two outputs. So again, you can see, this layer has three inputs. So three inputs and this has two outputs. This is again not desirable. Why is it not desirable? As I said, dimensions of input and output have to be the same. So again, this won't work for me either. Okay, so what is the third option? Third option says, okay, there are three inputs, there are two intermediate hidden neurons, and there are again three outputs. Okay, well, this seems good, right? I mean, there are three inputs, there are three outputs, and there are two intermediate. So I think this will work, because the input dimensions and output dimensions are same, and I have some chance, I have a fair chance to minimize the reconstruction error between these two terms, right? So I will say that okay, this will work. What is the fourth option? Fourth option has three inputs, one, two, three. It has three intermediate neurons, okay, and it has four output layers, right? So these four. So I mean, again, this will fail because there are three inputs here, whereas there are four outputs that are coming out. So I mean, the same logic that we applied here in the first option, the same logic will go here, okay, and hence this is also not a correct option. So this is an easy question. You just have to check, if the uh, if the dimension of input and output layers are same or not. That is the only thing that you need to look at, right? So this was the first question. So this is an easy question just to check, the basics that you know what an autoencoder actually does or not. Okay. Having said that, let's see the second question. So second question says, if the dimension of the hidden layer, if the dimension of the hidden layer representation is less than the dimension of the input layer, then what kind of autoencoder do we have? So it is saying the dimension of the hidden layer. Okay. So if I use h for the hidden layer, it is saying that dimension of the hidden layer h is less than dimension of the input layer, maybe x. Okay, this is what has been given to me. So what does it mean? So how should it so what should the neural net so how should the what should be the structure of my neural network? uh, I have some idea, right? I mean, it will have some, some inputs here. It will have some intermediate layers, but it will be strictly less than what the number of neurons that are here. Okay, so this would be less than this would this will be greater than this thing, and I will have again same number of outputs as the number of inputs. Okay, so this is how it should look like, and I think this something like this is called an undercomplete autoencoder. Why is the name so? The name comes because this is basically a neural network. End of the day, it is just a neural network. Okay, it can be trained using some loss function and things like that. But we are solving a problem of reconstruction, so this thing and this thing needs to be have to be of the same size. But we are bottlenecking it, or in some sense we are asking it to reconstruct. We are asking it to reconstruct the original data with something which is less than the dimension of the original data, right? Hence it is called undercomplete, because uh, the because uh, sufficient information might not be present here to reconstruct what is to be obtained here, right? So in that sense, since we have less information here and we want to create something which has a higher dimension here, it is called under complete autoencoder, right? So this will come under the category of something called under complete autoencoder. So there are other options as well. So this is the correct option, right? So there are other options as well. For example, we have an option called complete autoencoder. Complete. So maybe I will use some other color. So complete autoencoder. What does a so I will use AE for autoencoder, right? Just a short form for my convenience. So what is a complete autoencoder? Complete for okay. So let me write it down. Okay, dimension of H. Okay, yeah. So here I had dimension of H was less than dimension of X, the input, right? For a complete autoencoder, the dimension of H is equal to dimension of X, right? So what it says is that, okay, this thing which was this thing, the intermediate layer, which was less than the input layer that was here, this thing, if you make sure that there are enough neurons, it has same number of neurons as the input, it will be a complete, it will be called as a complete autoencoder. Okay, that's it. Okay, and then you have a over complete autoencoder, AE. In this case, what you have is dimension of X is actually greater than dimension of X. So you can imagine, you have a bigger network here. Okay, so maybe not this thing. So you have a imagine that you have a bigger intermediate layer here. Okay, something like this. So you are giving it information that is more than required to complete this to reconstruct your data, original data, right? So, in this sense, it is over complete, that you are giving more information that it is than it is required. Okay. So this is something called over complete autoencoder. And similarly, you have there is another option which is sparse autoencoder. Sparse autoencoder. So sparse autoencoder has a structure which is similar to that of overcomplete autoencoder, right? So if, remember that overcomplete autoencoder had some a structure like this, a bigger intermediate layer and smaller input and output layer. But it says that okay, though my dimension is big, I won't allow each of these activations, each of these outputs to be greater than one or less than zero. So each of these activation would belong to something between 0 and 1. So, so in some sense, it is adding a constraint to your representation that you are learning. It is saying that it should only be between 0 and 1. However, note that it need not be between 0 and 1, right? I mean, why should it be between 0 and 1? Uh, so we are constraining our representation to have values between 0 and 1 only. However, we are saying that, okay, since I have added some restriction to it, to get better performance, what I will do is I will, allow it to have a dimension that is greater than that of the input size. Okay, this is what we call as sparse autoencoder. But so why is such an autoencoder important? Because working with something which is between 0 and 1 is much easier. I mean, if you have learned if you have seen something in neuromorphic computing and things like that, if you want to deploy something like this on a actual system, which is hardware and all those things, it is easier to work with some values between 0 and 1, and it is easier to deploy things. That is why sparse autoencoders can be useful as well. So nonetheless, in this case also, dimension of h will be greater than dimension of x, right? Hence, I mean, these three options won't work. You know, this won't work, this won't work, and this won't also not work. So under complete autoencoder is what the correct answer is, right? So this is the basic gist of this thing, right? Okay. So, I mean, if you have any question at any point of time, you can either just unmute yourself and ask question, or you can also write in the chats. Okay. Okay. So here is the third question. Third question says that suppose for one data point we have features x1, x2 till x5, but it is given to be this is given to be -1, 2, 3.2, okay, minus 5.6 and 0. Okay, so these are the five features that we have been given. Okay, so this is my x. Okay, so this is my x, right? Then which of the following function should be used in the output layer decoder? Okay, so let us look at the options, and I will, maybe that way I will explain why particular option is not correct. Okay, so the first option is logistic. So remember the structure of the autoencoder, which was this. Okay, remember that you had something. You had in case I forgot to say, this part of the autoencoder is called the encoder, and this part of the autoencoder is called the decoder, right? So in some sense, you are encoding your data here, and you are encoding your data in the form of text, and here you are decoding the data and reconstructing the data. So the question says that in the decoder part, which is this part, right? The which activation function f should be used to reconstruct this data that we have been given, right? So here, so let me, what I will do is maybe I will copy this diagram so that maybe it is easier for us to visualize things. So copy this. I will just paste it here, minimize it a bit. Okay. Yeah. So just for reference, I will keep this thing here. Okay. So we are asked that, okay, what should be the this function f? So remember the logistic function. What was the logistic function? So f of x would be 1 upon 1 plus e raised to minus w transpose x is what the logistic function is, right? uh, Remember that the range of this so how does this logistic function look like? The logistic function looks like something like this, right? So you have something like this between 0 and 1, something like this. So you have 1 here, so it is upper bounded by 1. The logistic function goes like this, right? Something like this. So one thing that I am sure about is that logistic function will give me value only between this in this range, right? 0 and 1. So in other words, what I want to say is that f of x will always belong to 0, so open brackets, not close, 0 comma 1, right? This is all I can say. However, okay, so what does it mean? That okay, whatever this value is, okay, whatever I calculate here, the output, so when f is applied to this, the output will belong to 0 comma 1, right? This is what I know. So is my data between 0 and 1? So I mean, this is the reconstructed data, right? So if I'm reconstructing my data, then I should expect that the range of my reconstruction is same as the range of my input data. However, we can see, that the values here are like 3.2, minus 5.6, 2, and similar things, which which do not, so 2, 3.2, minus 5.6, these do not lie in 0 comma 1, even minus 1, right? So hence, a choice of logistic function, it will not be a good idea, right? I hope you get my point. This is a simple thing. Just I'm, thinking aloud my whatever my arguments are. Okay. So what is the next option? The B option is a ReLU. Okay. What is ReLU? ReLU, it, the function ReLU is looks like something like this, like this. So it is of max of 0 comma x. Oh, sorry. This thing. How does it look like? It looks something like this. So you give something as input to it. Whatever it will do is, when x is negative, when x is negative, it will continue to give 0 as output. Okay. However, as soon as x becomes positive, it will give you whatever the value of x is. This is what the ReLU function is. So what I know, so from here, what do I know? I know that f of x will, the ReLU function will always give me something between 0 comma infinity, right? So, or in other words, this is also called R plus, that positive part of the real line. Okay. It won't give me anything which is negative, right? So does my data contain anything negative? Well, yes, minus 1 and minus 5.6 are something which are negative, right? And hence, so if I use this ReLU function as my activation function, I would never get minus 1 or minus 5.6 as my output, because ReLU will not give me anything which is negative, right? Hence ReLU is also not a good choice. I hope you can see that, right? So okay, so what is the third part? C. C is softmax. Okay. What was softmax? So as the course progresses, maybe these things will come to your mind immediately. If not, maybe just keep up with the course. Okay. So what was softmax function, right? So softmax function, what it does is that it will say that okay, the output of a particular neuron in this output layer, so maybe this output, what will it be? It will be e raised to minus wi trans wixi, okay, upon something summation over I e raised to minus wixi. So maybe use j here, sum over j, right? Something like this. This is what the softmax function is. So here also you can see that uh, I can, what I can do is I can write this as e raised to minus wixi upon e raised to minus wixi. So I am using the correct, that particular ith index, right? Plus the rest of the summation j not equal to I e raised to minus wj xj, right? And I can see that what does it look like. So this looks, so I mean, if you agree with me, this will be 1 minus uh, summation j not equal to I e raised to minus wj xj upon summation, the whole summation, right? Summed over all the things e raised to minus wi xi. So this comes out to be like this, right? Why does it? So imagine this was a number, this was some number 2, okay? So this is also 2 because the both are same, and this maybe is some number 3, okay? So what this entire fraction will become is 2 upon 5, right? And I can always write 2 upon 5 as 1 minus 3 upon 5, right? And this was 3 was this entire summation which I have written here, okay? So I hope you can see what I have done. I have just done some simple maths. So, and I also know that 3 by 5 is a positive number. Why? Because exponentials can never be negative, right? So I am subtracting something positive from 1, right? So it will always be less than 1, right? So I hope you will agree that this will be less than or equal to 1, right? Because why? Because this part is greater than 0. So I am subtracting something positive. Maybe this value is like 0.1. If I subtract 0.1 from 1, it will become zero point 0.9. So which is less than 1, right? So f of xi, I know that is less than 1. So what do I know about softmax? That each of these outputs, right here, all of these will be less than 1, right? This I know. So do I have anything in my data which is greater than 1? Well, yes, this 2 and this 3.2, these are, both greater than 1. So I have no hope of, you know, uh, I have no hope of, reconstructing these data points. So whatever this value is, what f will do is it will, restrict my outputs to be less than 1, and hence these 2 and 3.2 I will never be able to reconstruct, right? So having said that, so this is also not a good option, right? I mean, I hope you can see that. What is the last option? The last option is linear. Okay. So what is linear? Okay. So what is linear? Okay, linear. So linear says that f of x is some wx. Okay. Well, here I had some f. So here f of x is wx. Let me write this down, right? So for me, so f of what we had there, w star h plus c, right? What will this become? W times w star h plus c. What will this become? W star plus h plus wc, right? And I can write this as some w dash h plus some c dash, right? This is what it is. So eventually, using a linear activation function is nothing but similar to applying some linear transformation. So does this have any bound on its range? So I mean, in 1D, this is just a line, right? I mean, in 1D, this is like mx plus c form, right? And what is a mx plus c form? It will just be a line, right? I mean, it will just be some line which cuts things at something like this. But you can see that in the range, it covers everything. It covers the positive part as well as the negative part. So, I mean, this works, right? Because my data features that I had are actually, they are, this can be anything. Sometimes it is taking negative value, sometimes it is taking positive value, sometimes it is also taking value as 0. So I don't know anything about like the bounds on my data. So it is better to, keep my options open. So this looks like a good, this looks like a good thing to use, right? So linear function will work because my data can be reconstructed using this linear activation function, right? Uh, so I hope that I was clear. If not, maybe you can ask question by unmuting yourself, right? So this was the third question. moving on. So you can see these questions are not, these are just, common sense that what should be this? If this is my desired output, what should be my activation function? And this is basically just engineering, that you are manipulating your activation functions or whatever you have according to your use. Okay. So if that is clear, what I will do is I will move to the next question. Okay. So here is the fourth question. What is the fourth question? Which of the following statements is true with regard to overfitting in over complete autoencoders? So we have something called over complete autoencoder, right? So how does an what does an what is the structure of an over complete autoencoder? So it looks something like this, right? So you have some inputs, but you have a representation or intermediate layer which has neurons more than the input itself, right? And then you have some reconstructed data, right? This is how an over complete autoencoder would look like, right? So what can we say about this? Okay, so there are options. So let us look at the options one by one, right? So the first option says the reconstruction error is very low while training. Is this true? Well, let us have a look at it. So let us think of something simple. Okay, since I know that there are more number of neurons here, is it possible that I can memorize this thing? Well, it is right. That so suppose there this is so let us imagine that this is so let us imagine that this is some R6, this is R10, and this is again R6, right? So 6 neurons as inputs, 10 intermediate neurons, okay, and again 6 neurons as outputs, okay. So the reconstructed data. So what I can do is that amongst these 10 neurons, so amongst these 10 neurons that I have here, what I can do is I can select any six of these, right? Any six of them, and say that okay, I will just copy these six neurons into this six intermediate neurons, right? So I hope what I am saying is true. So what I will do is that you know what I will do is okay, I will say that okay, just copy this neuron here, copy this neuron here, copy this neuron here, and similarly copy this neuron somewhere here. Okay, and I will say that okay, since I want to reduce my reconstruction error, what I will say is that okay, now since I have to reconstruct, and so in the rest of the data, whatever representation is, I won't care that whatever it might be, I don't care whatever what it is. So I don't give a shit about it. Okay, so so while reconstructing it, what I will do is I will say that okay, I had copied these data points, okay, here, right? What I will do is I will just since I have memorized these inputs here, so since I have memorized these inputs here, right? I will do what I will do is I will just say that okay, whatever you have memorized here, just put it here. Whatever you have memorized here, put it here. Whatever you have memorized here, put it here. And similarly, whatever you have memorized here, put it here, right? I mean, this is one way to reduce your minimization error. Is the minimize so sorry, reduce the reconstruction error. So is the reconstruction error minimized here? Well, yes, right? You copied these data points here and you just copy pasted it again here, right? So there is actually zero reconstruction error because you are reconstructing exactly what was given to you, and you don't care whatever here was. So what this is like of no use to you, right? So I mean, you are good, right? You have minimized your reconstruction error. So this option is saying something that is true, right? So this is a correct option, right? I hope you are getting my point. What was the second option? So the second option says that network fails to learn. So the network fails, sorry, fails to learn, fails to learn what? Good representation, good representation of input. Is this true? Well, we just saw that, what the network did was actually just memorize your data, right? It just memorized this thing and copy pasted it here. So it has actually not learned anything. I mean, so this part of the network was, just trash. You didn't need it. So there was nothing meaningful here, right? I hope you get the point. So this representation is actually useless for me. Why is it useless for me? Because it in some way just memorized your data and it didn't provide me any useful information additionally. So this is just a trash for me. This part of the network is just a trash for me. I hope you get that point. So this option is correct, right? Network has actually failed to learn a good representation. What it has done is actually it has memorized your data point, which was not desired. So this is also true. The third option is the opposite of this second option. Network learns good representation of input, which is a incorrect option. And the fourth option says that reconstruction error is very high while training. This is again opposite of this thing. So whatever. So the next two options are saying opposite of these two things. So that are obvious. So if these are correct, then the other two are false, right? So I hope the idea was clear. If not, just ask questions. Okay, here it goes the fifth question. So what is the fifth question saying? Fifth question says that okay, suppose we build a neural network for a five class classification task. So we have a five class classification task. Okay, right? Suppose for single training example, the true label, the, so we have been given some true label. So I hope you remember that these labels are given in form of one hot vectors. So it is 0, 1, 0, 0, 0. So what it means is that, the second class is the correct option. The others are, incorrect. Okay. So this input data point belongs to second class. This is what it means. While the predictions by the neural network are, what is the, okay, so predicted label. What is the predicted label? So it is 0.15, 0.2, 0.3, 0.15, and 0.2. This is what it is. What should be the value of cross entropy for this example? Okay, good. I mean, so we are just asked to, calculate the cross entropy loss. Okay. So for this, what we need to know is the expression for the cross entropy. What was it? So that was something like this: minus negative summation of pi log of pi hat. Okay, this was the expression for cross entropy, right? I hope you remember this. So where pi is the pi are the true labels. So this part, okay, so this part is actually pi. So this is the pi, okay, and pi hat are the predicted labels. So these are the predicted labels. This will be my pi hat, right? So what I will do is I will just simply substitute the values, right? Simple maths. So what will it be? So for the first is so negative. I will keep it in outside some bracket. Zero times. So this is zero log of 0.15. Okay, plus one one times log of 0.2. Okay, but others are also zero, so this will be 0 log what 0.3, this value, plus 0 log 0.15, this value, plus 0 log 0.2, right? So I hope you will agree that the terms which are multiplied by 0 are actually just 0, so they will not matter to us. This will go out. So what is the final thing? This is negative log of 0.2, and I can write a negative log of, I can write zero point 0.2 as so something like 1 by 5. So this is with base 2, right? And so this will become log with base 2 5, right? And if I remember correctly, so log 2 log 5 with base 2 is around something around so 2.3, right? Something around. I don't remember exactly, but it is something around 2.3. So maybe I will write approximately. Like approximately. So this was simple calculation, right? Nothing fancy here. Just a simple maths. Just substitute the values. You can use log calculator to calculate the log values if you're not comfortable with log, that is allowed, right? So simple thing, no, nothing fancy, right? Simple maths. Just you have to identify what the expression in the formula and what is given to you are how they are related to each other. If there is any doubt, you can ask questions, right? So moving forward, what is the sixth question? So sixth question is saying that okay, we are using the following autoencoder. So there is some autoencoder architecture. Let me draw it. So there are five inputs: one, two, three, four, five. There are two hidden layers: one, two, and there are five outputs: one, two, three, four, five. Okay. So this is your autoencoder. Okay. The eigenvectors associated with covariance matrix of our data. Okay. So do you remember what the covariance matrix is? So we saw it last time exactly, right? So if you remember the covariance matrix C, remember what we did last time. So it was something like x minus mu into x minus mu transpose, right? And we actually, I think, also normalized it by some factor, but yeah, I mean, eventually I think this was what it was. I don't remember some normalizing, but yeah, I mean, this was what it was. Okay, so this was broadly the covariance matrix, right? And okay, so this has been given to us. Sorry, this is not given to us. We are what we have given is that this has eigen vectors. Okay, eigenvectors for these this covariance matrix is given to be what v1, v2, v3, v4, and v5. Okay, what are the representations most likely to be learned by our hidden layer h? Okay, so this is the hidden layer, just remember that. And also we are given that this is a linear encoder and linear decoder, right? So what does it mean? It means that so this mapping is by so this was a uh, some weight matrix W, and this was obtained using some another weight matrix W star. G was the activation function here. F was the activation function here. What we are given is that both these G and F, these are actually linear. This is what has been given to us, right? So so what does it? So in the lectures, if you saw, we can actually relate PCA with autoencoders. How? So so here was the conditions that were there. I will just repeat those things for you. So an autoencoder acts as PCA if what are the conditions? The first condition was that encoder is linear. Okay, decoder decoder is also linear. Okay, third condition is that MAC loss is used for training. This was the training. Okay, third condition. And fourth was that your data uh, X or your input is normalized. Okay, this is what these were these like the four conditions that were required to for an autoencoder to act as a PCA. So let us see if these conditions are being satisfied, right? So the first condition, that encoder is linear, that is true, right? Because your G is a linear activation function. So if you use a linear activation function, eventually what you will get is a linear operation, right? So encoder is linear, okay. Your decoder is linear, okay. That is also true because F is also linear in this case, right? Uh, uh, it is not. So MSc loss is being used for training. Well, I mean, it has not been mentioned in the uh, uh, question itself, but in general, whenever there is a general autoencoder question, we will assume that MSc loss is being used. So that is something that we will assume that okay, this is assume. I mean, in general, whenever you solve autoencoded question, this is always true, unless and otherwise mentioned to you. Okay. And the fourth option is that X input is normalized. So this also we will assume. Okay. Uh, this is also something that so these two conditions is in whenever you are solving, this is assumed to be true. This is assumed to be true. So all the four conditions are being satisfied, right? So all of them are correct. So this autoencoder will actually act as a PCA, right? So let me write this down. This will act as a PCA. So if you remember, if you remember from lecture, what is the activation function that you will learn here? So what is the weight matrix that you will learn here? W, what will it be? If you remember, it actually comes out to be something like, uh, you know, uh, uh, so if W is there, so this comes out to be V times, so I think it becomes, yeah, so it becomes V times X, where V is eigenvector of X transpose. So if so just to clarify, if the data is normalized, this part, right, this part will become simply X transpose, right? Because it is normalized, right? So you have already subtracted your mean from the data. So this will become zero, this will become zero, and eventually it will become X transpose. So, and your weight matrix that you are learning, sorry, so this will be just V, right? So, yeah. So what I'm saying is that this is the eigenvector that you want. So in PCA you use the eigenvectors of this covariance matrix to do projection. And what you are getting here from V is also eigenvector of X transpose. So both of these things are same, right? The eigenvectors of C are V. So let me just write it down. It means that the W vector, this W vector that you are learning here is eigenvector of what? The covariance matrix C, which is equal to X transpose, right? And since your hidden dimension is just 2, you will use the first two eigenvectors here, right? So what are the first two eigenvectors? V1 and V2, right? So eventually what the V will look like is something like this, right? So it will have V1 as first column in your matrix and V2 as a second column in your matrix. That's all, right? So this will be some n cross 2 matrix, right? Only then it will give you, only then it will give you a two-dimensional hidden layer, which is here. So having said this, so basically V1 and V2 is what you will learn using your eigenvector. So the question asks you what are representations most likely to be learned by our hidden. So the answer would be V1, comma V2. All the other options are incorrect. V4, V5, V1. Why V1, V2? Why not V4, V5? Because we look at the first two eigenvectors. So we look at the eigenvectors with maximum eigenvalues, and it has been given to us that these eigenvectors are written in decreasing order of the eigenvalues. So V1, V2 have top two eigenvalues. So we will use V1 and V2 as our representation, not V4, V5 or V3, V4 or anything like that. Okay. So if you have any doubt, please ask. If not, we will move forward. I mean, since you since there are not a lot of questions today, I am just assuming that you are understanding things, and I am moving forward that way. Okay. So this was the sixth question. Let us look at the seventh question. Which of the following statement is always true with respect to regularization in autoencoders? Okay. Let us look at this. So So let us look at the options that we have been given. So the A option is uh, regularization. I will just write REG. Regularization shrinks the size of weight vectors. So is this true? Well, I mean, so if we remember what a regularizer means, okay. So for example, so what it means is that while training a, so there is some loss function that you use for your autoencoder. Let's call it LAE, okay, L autoencoder, loss used for autoencoder. It is generally some reconstruction, REC, reconstruction loss, plus some lambda times, L regularization, REG, okay. So this is a regularized autoencoder. This is what we mean when we say, regularized autoencoder. So this reconstruction loss could be anything like MSC loss or something like that. Okay. However, L regularization is something that depends on what we want. Okay. So, so this can be definitely achieved. Regularization shrinks the size of the weight vector. So if I, if I take LREG that is mentioned above to be, norm of theta. So norm of, maybe I will write norm of W whole square, something like this. If I use something like this, so this is the weight matrix to, calculate the hidden layer representations. If I use my regularization loss to be this function, then what I'm saying is that, whatever you learn, okay, whatever representation that you learn, I don't care, but the weight vector that I am using should have a norm, should have a length which is, very it should have a small length. That is what I'm saying. It should not be like very big, something. So it should not be very something like this. It should be something small. This is what we are saying. So this can be achieved. I'm not saying that it cannot be achieved. It can be achieved. However, so the question, however, asks us something which is true for all the regularization autoencoders, right? This is only true for this particular loss, regularization loss, right? This is not true for all the regularized autoencoders, right? This statement is true only for this. However, it need not be true for any general regularized autoencoder. Hence, this is not this won't be a correct option, right? So coming to the B option, what the B option says is that, okay, regularization reduces the search space of weights for the network. Okay, regularization reduces search space of weights. Wait, GHT, something like this. Okay, so is this true? Well, I mean, it is actually true. Why? Let me illustrate it using some example. So suppose the weight matrix was in R2, okay, and you were using some, reconstruction loss as you said. So earlier, this, let's say this was, so let's suppose that this was W1 and this was W2 something. So earlier you were allowed to, search in whatever. So earlier your weight matrix could take any value. It can be here, it can be here, it can be here, or something like that. However, let us assume that, you say that, okay, I am going to use this L regularization, which is norm of W square. So what will it say? I mean, if I use norm of W square, what it is saying is that, you cannot go arbitrarily far enough. You cannot go something somewhere here, somewhere here, somewhere here, somewhere here. You have to be close to the origin. This is what this regularization would mean, right? So this is what it would mean, that, okay, you can go anywhere, but you need to be inside this circle. Is what a loss function, a regularization loss like this would mean, right? This is what it would mean. So I hope you get my point that, regularization actually constrains your search space. Now you cannot go arbitrarily anywhere, here, or here, or here, or here. You need to be inside some circle, or at least you need to be close to origin. These points need to come to origin. Otherwise, this loss function won't be minimized, and the training won't happen. Hence, this is a correct option, that regularization reduces the search space of weights. Okay. What is the third option? Third option says the encoder is sensitive. Sorry, okay. This it says that regularization helps to reduce the overfitting in overcomplete autoencoders. Okay, what is saying that regularization helps reduce overfitting in over complete autoencoders. Is this true? Well, I mean, regularization in general is used for to avoid overfitting, right? I mean, the the concept of regularization was first coined, just to achieve this, that we want, to reduce my overfitting. So this is also true, right? So what it is saying basically is that you have a overcomplete autoencoder. So you have some input, you have a larger hidden representation, and again some output. As we saw earlier, that this thing can actually just copy the data and just paste it again. But let's say you use some regularization. For example, you say that okay, these outputs cannot be, should always belong to something between 0 comma 1. So this is what we call sparse autoencoders. Now you have constrained your network. So if your original data was, let's say belong to our general real line, okay, so R3, let's say. Now you can, so it could take any value, let's say, -5, -100, -200, +200, something like that. Now you are saying that but my representation should only contain values between 0 and 1. Well, now, if you add some regularization like this, now you cannot simply copy paste, right? I mean, copy pasting won't be possible now because you cannot copy. So this won't be, you won't be able to copy this thing here because these values can only be between 0 and 1. These can only be between 0 and 1, 0 and 1, while these belong to, a real line. This is not possible anymore if you add some regularization. So yes, I mean overfitting basically means memorizing the data. So this is also true. So you have avoided overfitting in this overcomplete autoencoder. So this is also correct. The fourth option is all of these. Well, the first option was not correct, so all of these won't be a correct option, right? So I hope this was clear. So this was simply to make sure that you know what regularization in autoencoders mean. Okay. Coming to the eighth question. What is the eighth question? It says, which of the following statements is true for contractive autoencoders? So now we have to deal with something called contractive autoencoders. What is it? So in contractive and autoencoder is again a regularized autoencoder. So you have LA, which is equal to L time L reconstruction loss plus uh, lambda times L what L regularization reg. And for contractive autoencoders, this L regularization, what is it? It becomes Frobenius norm of Jacobian matrix J, the Frobenius norm of it and square of it. So what is J here? J is basically a matrix. Okay, so if x1, x2, x3 are your input and h1, h2, h3 are your learned representation, this matrix has del h1 by del x1 as first entry, del h1 by del h2 by del x1 as second entry. Similarly, del hn by del x. Sorry. I think I did a mistake. I'm sorry. So this was, I think, h1 only. This will also be h1 only. The differentiating term will change del xn. So xn is the dimension of your input. Okay. The second row will be del h2 by del x1. Del h2 by del x2. Similarly, till del h2 by del xn, and so on, right? So this is what it will look like. So Jij, the ijth entry of this matrix will be del hi. Okay, so Let me just come. Yeah, del hi by del xj. This is what the matrix will look like. Okay. So, and what will be the Frobenius norm of this? The Frobenius norm of j, the square of it will be, squares of these things. So del h. So let me write it in a concise form. Summation over I comma j del h I by del xj square of. This is what the Frobenius. So this is the loss function that we will be using. So let us think about it. So if I want to, so let us take one term, okay? So let's say del h1 by del x1. So what is it? It is the rate. So derivatives, you can look at it as rate of change. So it is what it is, rate of change. What is the rate of change with respect to rate of change of h1. So h1 with respect to x1, right? This is what it is. Now I'm saying that this should be small, right? Well, if I'm saying that this should be small, what does it mean? So it should not be sensitive. You're sensitive to x1. This is all it means, right? So I'm saying that h1 should not change a lot with x1. Okay, that is what I'm saying. So what I'm saying is that let x1 change whatever in whatever manner it wants to, but h1 should not change a lot. H1 should sort of stay wherever it is. This is what I'm saying. So this is what it means, right? So, but I mean, in lectures also it was mentioned that if I am using a regularization loss, which looks something like this, isn't it contrary to what I am expected to do? For example, I mean, in reconstruction error, what I would like is, if x1 changes, I would like my representations to change, right? So on one hand, I am asking my reconstruction loss to be sensitive to everything that is everything that is there in the input. On the other hand, in the regularization, I am saying that okay, don't be sensitive to any of this, right? So these are two opposite losses, right? I mean, one loss is saying that okay, be very sensitive. Another loss is saying okay, don't be very sensitive. uh, uh, Stay constant wherever you are. Okay. So what would such an autoencoder learn? The thing is that so so here is the thing. What is the problem with being sensitive to the all the inputs? Okay, the problem here is that if even if there is some noise in the data, okay, so if even if you ask, so let's say there is some x1, so x1 has input, and you add some noise to it which is very less. If your representation is very sensitive to your input, then your representation that you will learn for the noisy data will be very different from the representation that you will learn for the original data, right? So what I am saying that, so let's say h1 is the representation for x1, that input, okay, and h2, so let's call h1 bar is the data, is the representation that I learned from x1 bar, which is nothing but x1 plus some noise, x1 plus eta, where eta is very small, okay, it is almost negligible. Now I what so the reconstruction loss, what it is saying is that these two h1 and h2 should be very different. Since you are very sensitive to your input, your representations are very different. However, is this what we want? Well, no, right? This is not desired. We want h1 to be so I want distance between h1 and h1 bar to be less than some epsilon, some, I want it to be very less, I don't want to be very high, right? But this is not enforced by this reconstruction loss alone. Hence this type of regularization loss that I have mentioned here, what it will do. So on the other hand, if I just use this this regularization loss that I have mentioned here, what it will do is that it is not sensitive at all. So even if this eta is very high, if I have added a lot of noise, it will say that okay, well, since your representation was not very sensitive to your input, it is these two are still close to each other. However, this is also not desired because my input now looks very different, but I'm saying that though my input is different, the representation is the same. So I hope you can see the contrast between these two loss components. So what will be the middle ground? So the middle ground. So just let me write this. The middle ground will be that learn only the important important slash necessary uh, variations in the data. So L reconstruction was saying, okay, even if it is, if even if the input changes by a little, change it, your representation should be very different. Well, that was not desired. L regularization was saying that even if the input changes by a lot, don't change. That was also not desired. So what we did was we just added these two, and hence what it will do is that hopefully it will learn only the important variation that are present in the data, right? So among the given options, the first option is that uh, we add noise to train this encoder. The first is add noise to train the encoder, the AE. Well, this is not correct. We don't do anything like that. The B option is AE is prone to overfitting. Overfitting. Is this true? Well, no, because we are using some regularization, right? So regularization is there to prevent overfitting. So this is also not correct. The third is encoder. The autoencoder is sensitive, sensitive to any change. Well, this is not true. This would have been true if we just use the reconstruction loss, but we are not using just the reconstruction loss, right? We are also using the regularization loss, which is the Jacobian norm, Frobenius norm of the Jacobian matrix. Hence, this is also not true, right? I mean, since we have added this regularization, it is not true, right? And finally, there is a D option. What is the D option? It says that autoencoder picks only important variations. Is this true? Yeah, well, this is true, right? I mean, as we explained this thing here, this is exactly what it does, right? So the D option will be correct. So, so this was the explanation for this eighth question. If you have any doubt, let me know. Otherwise, I will move forward anyway. Okay, so I hope you get the point. What? So there is a chain of logics basically, right? And you just need to remember. You need to get used to with this chain of logics, and hopefully you will be doing good in your exams and quizzes, right? So moving forward, the ninth question, we are given an autoencoder A. So there is an autoencoder A. Okay, the average activation of the neuron in this network is 0.001. So what it is saying is that, there is some autoencoder. Okay, some autoencoder. Let us assume as it is an undercomplete autoencoder. Okay, something like this, and this is the H. Okay, what we are saying is that you know mu. Let mu denote the averaging option. Mu of H is what? 0.001. This is nothing. This is actually 10 raised to minus 3, right? 1 by 1000. So it is very less. So amongst the autoencoders that we have learned uh, in our in these lectures, right? Uh, which autoencoder do you think this property is close to? So if you remember, so okay, let us. So if you even if you don't remember, for example, let's say you don't remember, let us look at the option. Options will help us. So first is contractive autoencoder. We just saw what contractive autoencoders are. So do contractive autoencoders force the hidden representation to be small? Well, I mean, it says that okay, it should not change a lot. I mean, it basically picks only the important variation in the data. It never says that you should the the value should be very small. So this is not correct. I mean, contractive autoencoders never enforce this thing, right? I mean, we didn't see anything like this. Okay. So here is, so what is the second option? It is overcomplete autoencoder. Does an overcomplete autoencoder enforce small activations? So there is some auto. So instead of so let us imagine that this was an overcomplete autoencoder, meaning that there are lot more number of neurons in the hidden layer, right? So does this does this enforce the neurons to have lower activation functions? Well, no, right? I mean, again, we cannot, there is nothing that tells us that the activations here should be low, right? So this is also not a correct option, right? Well, moving on, what is the third option? C option is sparse autoencoders. Auto sorry Sparse autoencoder. So what does a sparse autoencoder do? Well, the special property about sparse autoencoder is that the function g of the activation function g of x is a logistic function, right? So this is 1 upon 1 plus e raised to minus w x, something like this, right? Well, so this we know that belong. So as we have been seeing, this I have drawn this diagram a lot of times, but we should remember that logistic function looks something like this. So we know that it belongs to 0 comma 1, right? So we know that this is one autoencoder that enforces the representations to be between 0 and 1. That we are sure of, right? So it is possible, since the values are between 0 and 1, that your activations are small. Why? Because let's say there are lot of neurons here, and you are take all of them are between 0 and 1, 0 and 1, 0 and 1. It is possible that the average is like 0.5, right? That is possible. It is also possible that the average is like 0.1. It is possible that the average is 0.9. All of these things are possible. However, we know that it cannot be more than 1 or less than 0, right? Because this particular loss activation function won't allow your representation to go beyond 1 or less than 0. Hence, sparse autoencoders are something that is it is possible for sparse autoencoder to have an average activation function between 0 and 1, and the given average is like between 0 and 1. It is 10 raised to minus 3. So it is possible that we obtain such uh, activation function, right? So this is possible. What is the D option? D option is denoising autoencoder. So what is a denoising autoencoder? So what a denoising autoencoder does is, let's say you have let's say you have four inputs here. What it does is it adds some noise to it. It makes it, let's say, again four, but it is a noisy version. So if this was x, this is x plus eta, right? Then it uses a overcomplete autoencoder. So there is a overcomplete. So you have this H layer which has a lot more number of neurons than the input, and then it reconstructs the original data, right? So this is what it is. Now, so this is fed to this. This is used to reconstruct the data. Again, here, is there any restriction on the hidden layer to have values between 0 and 1? Well, no, right? I mean, we have no restrictions because this value can be anything, this value can be anything, and hence the average can be anything. I mean, it can be high, it can be less. I don't know, but I mean, it does not force your activations to be very less or explicitly, right? So okay, I mean, this is also, so this won't be this is not a correct option, right? I mean, there is no restrictions on denoising autoencoders to have smaller activations. That is all I'm saying. So this is also not correct. So sparse autoencoders is the only correct option. Moving on. So there is the last question, 10th question. What it is? Possible applications. Possible applications of a autoencoder. What are the given options? So let us see. So basically some options are given and we are asked that are these correct or is not correct? Okay. So what is the first option? Data compression. Data compression. Well, what does data compression mean? If you remember, data compression means that you have some big data. Let's say you have a file of, let's say, 1 GB or like 1000 GB, something like that. Okay, but this big data cannot be used to, if you want to send this 1 GB data or 2 GB data to someone, let's say on WhatsApp. WhatsApp cannot handle such a large data. It will ask you to reduce the size of the file to in MBs, like maybe some 50 MB or less than 20 MB, something like that. So there are data compression means that you have some data. So let's say D is your data. So size, there is some size of data. You need to come up with some representation, H, capital H, which is less than the size of the original data, whose size is less than size of the data, but it captures the essential information that is present in the data, right? So can we use autoencoders for data compression? Well, I mean, I mean, if you use a undercomplete autoencoder, which is something like this. I mean, what you are doing is that you are using this data to construct a representation here, and you are reconstructing the data. So, is it possible that I can? So, can this be used for data compression? Well, here is one way that we can use it. How? What I will do is, so let's say someone, so this was a big data, right? Big data. Let's say this was, so let's say this was in R, like 10 raised to, so 10 raised to, let's say, 200, something like big data. Now this is something in, like, let's say R20, a relatively very less dimension, and this is again in R10 raised to 200. And someone says that, okay, I want the data from you. He says that, but I cannot give you this big data because I cannot forward it to you through WhatsApp or something like that. So what I will do is, what I will give him this representation, okay, whatever this is, and I will also give him this weight matrix that was here, W star. Will that work? I mean, that would work, right? I mean, I will say that, okay, here is the W star, here is the my R20 vector, smaller data that I'm giving you. Just multiply this W star with this representation and you will get your original data. So, I mean, in this way, I can transfer my data to, this guy, whoever is asking me, right? So, data compression is a possible application which we can use autoencoders for, right? So, if this is clear, the second option is extraction of important features. Extraction of important features. So, does autoencoders help us in extracting important features? Well, yes, right. I mean, the whole concept of autoencoders was based on, data, so reduction of dimensionality, reduction of data dimensionality. The whole idea was based on that. So, I mean, that is what is, in some sense, it was the whole motivation for autoencoders, that we wanted to, we cannot work with this entire data. So what we will do is we will create a representation for it, which has a lesser dimension and hence less size and all those things, which can be used equivalently. So autoencoders can do this thing, right? I mean, the whole motivation for autoencoders was that. So this is also correct, right? I mean, the option will also suffice. I mean, after the today's whole, like, discussion, I hope this is not something that you are doubtful of. I mean, this is something that you should be convinced by now. If not, let me know. Okay. The third option is reducing noise. Well, re- can we use it for reducing noise? Well, yes. I mean, so this setup that we saw here, this was denoising autoencoders, right? So denoising autoencoders can be used to, ultimately it is an autoencoder, right? So what are denoising autoencoders? So as I said, you have some data, you add some noise to it, you learn a representation for it using an overcomplete autoencoder, and then you reconstruct this data. So the reconstruction loss is calculated with this x, not this x, right? I mean, so during inference, what so you are so how will it be used? How will this network be used? You will be given some noisy version of the data, and you will be asked that, okay, remove the noise from it. So what I will do, I will take this noisy data, I will construct something like this, and I will, again reconstruct this. Since I have trained my network to, eliminate this noise component from here, I will get a denoised version of whatever the input is given to us. So this is also a, fair application. This can also be used. So I mean, all of these can be used. So the D option that is given, all of these will be the correct option, right? So I hope this was clear. So let me know if so this completes the this week's uh, assignments. If you have any question that is maybe it was not clear, or maybe you struggled with, or you want to ask something that is not related to this, you can ask. Okay. So is there any question? Maybe you can.
Um, uh, uh, Nick, I just wanted
Yeah,
to ask, this
yeah,
course,
yeah,
will there
yeah.
be any indication regarding or anything taught regarding how to do the implementation? Because when we go on to do research, we are like more interested in, how can we implement it and in what scenarios can we use what. So would this course be looking at that, or will it will just be covering the theory?
Yeah, so as far as I know, this is actually primer on deep learning. So as far as I know, there is no implementation aspect to it. I mean, I think they are planning to have some implementation exercise in the future versions of this course, but as of now, I don't think so. I am not sure. I mean, I think it is not there. But I mean, personally speaking, uh, as you said in research, I mean, I am also a research student here at ISC. So, I mean, just speaking from a personal experience, implementation is something that I don't struggle with. These aspects of deep learning, which is theoretical, is what we suffer through. Because nowadays deep learning has been a lot of hand wavy thing to do, because I mean, someone says and gives you a network, and he says that it works, and I mean, you say that okay, it works. So there is no guarantees and things like that. In my opinion, if you are asking from a research perspective, implementation is secondary actually. I mean, uh, getting to know the basics like these things are what is required actually. But yeah, I mean, asking your basic question, I think no, there won't be any implementation. But maybe you can. So I think there is a interaction with course instructor around 16th or 17th. Maybe you can, ask him there. Ask it in the Google form or whatever they have
Any
provided.
suggestive material or website you would suggest for the implementation to get quick hands-on regarding that?
Yeah, so in my opinion, there are PyTorch tutor. So I mean, so I had struggled with these implementation videos on YouTube and things like that. What I found useful was, if you go to PyTorch, so there is a framework called PyTorch, and so there are several frameworks like PyTorch and TensorFlow and things like that. If you go to PyTorch and kind of look at the there are many. There is a tutorial section under Python on Python's website, and it starts with very basic stuff like creating a simple neural network, how to create your optimizer and train a simple network for classification and things like that. I think that is a good starting point. I mean, it has helped me a lot, and maybe it can help you as well. So if you ask me, that is what I would suggest.
Okay.
I mean, people say, okay, go to some YouTube tutorial and things like that. But in my opinion, those tutorials, are not as good as are not as good or as straightforward as these PyTorch tutorials are. Yeah.
Okay.
So that would be
Right.
my suggestion. Yeah.
Okay. Thank you.
Yeah. So any more questions? Maybe you can ask.
So can I get the YouTube videos of these lectures? I mean, you're recording, right?
Oh, yeah.
So can I?
Yeah, yeah. So, okay, so let me again post it. I mean, I have been posting these things on YouTube. So I think there was some Excel sheet that was shared with you. I don't know if it
Yes,
was or
yes,
not.
it's there. If you see the, the whole, go to the course, then down below they have, I don't know the exact label they have given, but they have written that it's for the live presentations or live video, something like that. And then there's a link, and in that link, drive link, it basically opens a Excel sheet for
Yeah,
all the previous ones. Yeah.
right.
Yeah,
So,
yeah. Thank you.
you can use that to access the lectures. Anyways, I have posted. I have sent the link of the playlist in the chats. If you want, you can directly access them from there. Okay. So, any suggestions? I mean, was the session very monotonous? Was it bad? Was it good? If you have any suggestions, please let me know. Uh, I mean, that is also very helpful for me. If you find something was not good, maybe I will try to improve from next time. Yeah.
No, today's, I mean, I'm not very good at seeing all the videos, but today I think I was a little more focused. And last week I was the first time I joined, and last
Okay.
week I felt that maybe you were sort of going through did various attempts for a few questions to come to the right solution. So at that particular day I felt that maybe if you could prepare in advance of with the, because we have limited time, and sometimes the participant can get confused if multiple attempts are being made to solve a problem rather than the correct
Right.
one.
Yeah, yeah,
Yeah,
right.
but that was
Last
not
time
any
I think
serious.
there Yeah, yeah. Last time I think there was one question which I got stuck in, and I tried to, solve that problem from different perspectives. I think, yeah, I also agree that that might have confused some of the participants. Yeah, I will try to, I will try that that thing doesn't happen again.
No, no, it's
But
okay.
yeah,
I mean,
thanks.
I am a researcher as well as a faculty, so sometimes we do get confused when we are delivering. So, just a feedback since you asked.
Yeah, yeah, sure. Thanks a lot for that. I mean, yeah, 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 I agree that even I get so if sometimes if my instructor gets confused, I also find that something is not going correctly. People get confused. I agree with that. Yeah, but I thought that that was a simple question, and I in my mind I had an idea that I can solve it on the spot, but I wasn't able to solve it. Like most of the questions, actually most of the questions that I see here, I don't actually, I just see the questions and I think, okay, can I solve this or not? And if I can solve this, I don't explicitly solve it. I come here and just solve it on the spot. But yeah, my judgment last time was wrong, and I overestimated my skills. So yeah, yeah, you are correct. I will make sure of that.
Great,
Okay,
thank you.
okay. Okay, so I think we can end the meeting here. Again, these lectures will be uploaded. Thank you all for joining. Have a nice evening. Yeah. Goodbye.
Okay, have a good day. Okay, bye. Thank you.
Yeah.
Thank you.